Hi everybody, my name is Thomas Daltey. I'm an applied scientist here at Amazon AI in Vancouver, and today I'm going to tell you about convolutional neural networks and natural language processing. The video will be split in three parts. The first part focuses on convolutions. Second part will be on a specific architecture to do text classification using convolutional neural networks. And the third part is about how you would code that using MXNet and how to deploy it for a short demo. So what are the goals? The goals first is to explain what convolutions are. So we start from scratch at the basic level, show how we can handle textual data with convolution neural networks, which are usually more applied to images. And the third goal is to analyze a reference neural network architecture for text classification called CREP. It was from Xiang Zhang in 2015 at Facebook AI Research. And the last part is going to be to demonstrate how we can actually train and deploy such a model. So, convolutions, what are they? In 2012, these three gentlemen, Alex Richevsky, Ilya Sutskever, and Geoffrey Hinton, they published this paper about a network called AlexNet, which for the first time applied deep convolutional networks with efficiency, and they proposed it at the NIPS conference, and they applied it inside the ImageNet competition. So the ImageNet competition is about classifying images among 1,000 classes. So before AlexNet, the top 5 error rate was 25%. When they introduced their network, they managed to reach 16%, which is a massive improvement in a field that was kind of stagnating. So the reaction from the community was very appreciative. People were super enthusiastic about deep neural networks, and since then we've seen a flurry of examples and new architectures being proposed and always beating like state of the art. And now we're really like in a very fast-moving field. This gentleman here is Yann Lequin, is a director of AI at Facebook. And he actually started working on convolutional neural networks as early as the late 80s and 90s. And the problem was at the time it was too computationally expensive to train. So how is it possible now? Well, it's related to this graph. If you can guess what it is, it's actually also related to the price of Bitcoins, and it's the stock price of NVIDIA. So NVIDIA is producing GPUs, and with GPUs, contrary to traditional CPU architecture, you have hundreds or thousands of cores. And we'll see in a minute why convolutional neural network can take advantage of this architecture to be super efficient. NVIDIA just released a GPU called the Volta V100 that can do 120 teraflops, which is 120,000 billion operations per second. And to give you a point of reference, that was about what could the best supercomputer in 2005 achieve. So now you have a supercomputer you can buy as commodity hardware. So these advances in computer vision were applied to many different fields. So suddenly you don't have to be an expert in one field to be able to achieve state of the art. For example, you can do sea land segmentation to track erosion on coastal areas. You can do galaxy classification. Like the Hubble telescope is taking thousands and millions of images, and you can just feed them through deep neural networks to get accurate classification of these celestial objects. In medicine, you have application of deep neural networks in MRI, X-ray, surgical cameras. A lot of different areas have benefited from such advances. Well, so what is a convolution? The convolution, it's a convolutional layer. It's an operation which we can define as the cross-channel sum of element-wise multiplication of a convolutional filter, also called kernel or mask, computed over a sliding window on an input tensor, given a certain stride and padding plus a bias term. So that's like the English definition. I mean, how I would describe it. It has a mathematical definition as well. But here I want to show you an example so you can see what each part of the definition means. So let's say we have an input matrix. These are random numbers. It's a 3 by 3 or 1 by 3 by 3. So it's a flat matrix. And we're going to use no padding, and it's only one channel. Our convolution is going to be done with a kernel of size 2 by 2, and we're going to use a stride of 1, and the convolution comes with a bias of 2. So these numbers that you see here, these are the parameters of a filter. That's the parameters that our network is trying to train and to tune in order to achieve the task we want to. So initially they can be randomly initialized. So like here it's just random numbers I picked for the sake of the example. But these are the parameters that your network is going to tune and adapt in order to achieve the task you want it to do. So few definition. So the result of such a convolution, we call it usually a feature map. And we're going to apply our convolution here. So we do the element-wise multiplication. So here that's 1 times 2 minus 1 times 2 plus minus 1 times 3 plus 0 times 1, like you see here, plus the bias we've defined here as 2, and then you get a number. So the convolution on this window here with this kernel gives you this number. And then we're going to move our kernel with a stride of 1, and we're going to play it here. So 1 times 2, minus 1 times 1, minus 1 times 1, 0 times minus 1, and this gives us 2. And that's where our number goes here. And we continue like that. We go down, a stride of 1, start again, we get 0, we do it again, 1 times 1, plus minus 1 times minus 1, which is plus 1, plus minus 1 times 3, plus 0 times 2, which should give us 1. So that's how it works. That's the most basic convolution you can do. No padding, stride of 1, but you can get slightly more complicated ones. For example, we can add padding. So when you add padding, it means that if you want to, if you see here, by applying this convolution, or there is a difference in size between our input matrix and our output matrix, right? It's smaller because of the filter moving. There is one element in each dimension that's being lost every time. So if you don't want to have such a dimension reduction, what you can do is add padding. Padding is to add zeros, a certain number of zeros on each of your dimension, and that way you can get you can keep the same dimension from your input to your output. So, and you can play with stride as well. So if instead you actually want to reduce the dimension of your output, then instead of moving just by 1, you actually can move by 2, 3, 4, whatever you want. So here it's an example where we move 2 by 2. And you can see the output is smaller than the input because we're moving further every time. So here we had used, there is part of the definition I said, which is we haven't used yet, which is a cross-channel sum. So what about if your input is multidimensional? Well, in that case, your kernel is not flat. It's not a 2 by 2 or 3 by 3 matrix. It's actually 3, for example, in that case where you have like 3 channel input, then your mask is actually 3 channel as well. So all this thing, that's one convolutional filter. You have one flat matrix per channel. So how did it work? We apply, as we said, the element-wise multiplication, which gives us a number. Then we do the same on each dimension of each channel. And then we do the cross-channel sum. So for each channel, we add together the number. Then we add the bias, and that gives us one number. So, and every time we get one number, and our output is going to be like 2-dimensional. It's going to be a flat matrix, even though our input is 3-dimensional. So when you read papers, you see, okay, we're going to apply 256 channels convolution. So what it means you actually have 256 different kernel like that, each of them with different parameters. Then you're going to get your output, and then the outputs, the feature maps are going to be kind of stacked together. So that's how you get 256 feature maps, one on top of each other. So that's a very important concept to get. It's because lots of papers, they always represent the network as a flat, um, in a flat manner, was actually a convolution done on a multidimensional input, like on a volume, like for example, if I show you the next slide, is going to be multidimensional as well. So keep in mind the kernel, if the input is multidimensional, the kernel is multidimensional as well. And that's true most of the times. We see an example, for example, for depth-wise separable convolution. That's not always true, but most of the time is true. So that's another representation where you can see how an entire input is actually like gives only one flat output. So I hope this is clear. It's quite important. It's something the first time I learned about convolution wasn't clear to me that the convolution, one convolution is applied to the entire input volume. So how do you count the number of parameters for one given convolutional layer? Well, you have this formula. Basically, you need to take the number m, which is the number of output channel, so how many of them you're going to have, multiply by the number of input channel. So we're going to see for each convolutional mask is going to be width times height times width times the number of input channels, and plus m, which is for each output channel, you have a bias term. So these convolutions are actually comparatively bring a small number of parameters because for each layer, they across the entire input, the weights are shared, right? It's the same operation that you do and you slide across your image, and this gives you a nice translation invariance. That the property of a convolution is you apply the same operations everywhere. So if you have a pattern somewhere on the top left or somewhere on the bottom right, it's going to be captured the same way. So as you can see, convolution are very simple. They're just multiplication and additions, just a lot of them. So that makes them very easily parallelizable because also they are independent. So you could start the convolution from the last channel or the first channel. You can do it, you can split the computation within one channel. So every step is parallelizable. And that's why GPU gives such a massive speed up because they can employ all their cores to do these computations. So why does it work at all? Like so far, we've only talked about like adding and multiplying. So convolutions were used way before deep convolutional neural networks. We use them in computer vision all the time. You can specially crafted masks can be used to get certain effects. For example, a sharpening filter or edge detection. Um, this was used before to, for example, to get the edges, and from the edges you were trying to form shapes, and from these shapes trying to infer what's on a picture. Uh, when you when you look at actually what the convolution is doing, for example, AlexNet, if you look at the first uh, convolutional layers, which was applied on the RGB channel, so each mask was at 3 dimensions, so you can visualize them in the RGB space, just like on this slide. And what you can see is network learns automatically to perform like pattern detection. Like some colors will be more important, sometimes more like edges or specific patterns. And in deep convolutional networks, you stack these convolutional layers one after each other. So what happens is the first layers learn basic patterns, and the next layers learn to combine these basic patterns into higher level representations. And this is because the receptive field grows as you go deeper in the network. So that's an example here of what I mean is on the first layer, let's say you have a 3 by 3 kernel, so you're going to apply that. And then you're going to apply, let's say, another 3 by 3 kernel, but this 3 by 3 kernel will have the information of the convolution from the next site. So it's actually going to combine information for a wider area than the first 3 by 3 area of the first convolution. So as you go deeper in the network, what a convolution can see, which we call the receptive field, is growing. Um, I mentioned pooling layers, which are one of the very important components of deep neural networks, and as well as a convolutional layer. So usually when you apply a lot of convolutional operations, but then you want at the end to classify something, for example. So you cannot have your dimension to be very high, because then you're going to have an explosion of number of parameters in your last dense layer. So you need to perform dimension reduction, and max pooling is the tool for that. How it works is it's kind of similar concept as a convolution. So you have the concept of stride and kernel size. So here, for example, we have a 2 by 2 kernel for our pooling size. And within this 2 by 2 pool size, we're going to pick the maximum value. So in that case, 6. Then we're going to do the same with the next 2 by 2 cell, and then we're going to pick 8. Then we move with a stride of 2 again. I'm going to pick 3 and then 4. So just like that, we've actually reduced the dimension by 2. And we have 4 times less elements. And we have kept the highest values, because what you want is to keep the highest activations. For example, think about if you do edge detection, you don't really care that much about all the black space. You want to keep the edges, because that's what was the most activated. The fully connected layer, I won't go in details into that. That's a multi-layer perceptron. Every unit is connected to every other unit of the previous layer and keeps 1 parameter per unit. So you can see how it can have a lot of parameters very quickly. So for example, this one will have 3 parameters plus a bias, 3 parameters plus a bias, 3 parameters plus a bias, and so on and so forth. And when you imagine when you have, for example, 1,000 input units and 1,000 hidden units, that's automatically 1 million parameters. So I've spoken a lot about convolutions, but how to visualize them. So some people build some really cool visualization. For example, Adam Harley from CMU. And we're going to try that now. It's applied to a very common data set that is used called MNIST. We're trying to identify which number we've drawn. So here you can see I drew 3, and it's represented in a matrix representation in a grayscale values. And then a first convolutional operation is applied, and the brightest points you can see here are the most activated elements. It's like when you look at the the filter on the right, which is the convolutional filter, and on the left, that's the input image. So as we, for example, here, you can see that okay. So this is applied in the case of a very common data set called MNIST, where we're trying to identify digits. So here I drew a somewhat looking number like a 6, and you can see that the first layer represents the feature maps after 1, 2, 3, 4, 5, 6 different convolutional um, masks. So we have a feature map or output channel number of 6, and that's what we get. Then we perform a max pooling operation to get this reduced size feature map. We use another convolution operation, and then this again through a feature map. all these elements are passed into a fully connected layer. So you can see all the connections here, and then another fully connected layer, and finally an output layer, which has a number of different classes we're trying to classify. So in that case, the 10 digits. So what's interesting to look at is, for example, if we look at this particular image, you can see that on the left you have the input image and on the right the filter. And the filter here has a diagonal pattern. And you can see that the activation on this filter map are showing the diagonal information. So basically, the network has learned that if something has like some like diagonal pattern, then it's going to be useful for classification later on. Then we can look at a video that has same concept but animated. So you can see each of this number, then is you have like a 5 by 5, 25 different convolution applied. The convolutions are passed into a pooling layer, so you have the max pooling. And then I think it's representing like the fully connected layer and then the final output. So that gives you an idea of how it works like a convolutional network. The numbers pass through the convolutions and then max pooling and then fully connected. Okay, so these were very simple networks, like a few convolution, a couple of fully connected layers. But the state of the art now is much more complex. For example, that Inception v3, I'm not going to go into detail, but you have a lot of different type of convolutions. You have new layers like batch normalization. You even have in this one an auxiliary classifier that's going to help bootstrapping the network. So there is a lot of advances that make this possible to have like deeper and more complex network to be able to achieve higher and higher precision and accuracy. So you can see deep networks means lots of layers, means lots of parameters. So you need a lot of data to train effectively a deep neural network. So before we move on to the next part, I want to speak about a few different type of convolutions that you might encounter when reading about deep learning. So you have the dilated convolutions, which is when you're trying to increase the receptive field. So when you're doing your convolution, instead of doing it on the contiguous uh, cells, you actually add holes. So some people call them convolutions à trous for the French, with hole. Then you have the transpose convolutions, which is when you actually add padding between your elements, and that's to increase the dimension of your output compared to your input. So you do that, for example, when you want to do super resolution networks, where you take a small image and you want to have like a higher resolution image without losing like the fine details. Another type of convolution, which is used a lot as well to reduce number of parameters, are depth-wise separable convolution. So instead of applying all the convolution across all the channels, you only apply the convolution on specific input channels, and then you combine them afterwards to get the right size of output. And that's useful to reduce number of parameters, which is much smaller, and make it more suitable for application like mobile or embedded devices.